You probably know that 0.9 repeating is equal to 1. If not, here is a short proof. The number line of real numbers contains all real numbers and is continuous. If 0.9 repeating wasn't equal to 1, we would be able to fit a number between them. There is no number greater than 0.9 repeating and smaller than 1, so they have the same value. But what if we had a number with infinite 9s to the left of the decimal point? Some might say that it is just equal to infinity, but this number is actually equal to -1. This type of number is known as p-adic number, where p denotes the base in which it is written. P in fact stands for prime, but for this example we are using 10 as our base. We can perform arithmetic operations on p-adic numbers. For example, we can add 1 to this number. We get 0 in the first digit, and we carry the 1. We get 0 in the next digit, and we carry the 1. This number consists of infinite 9s, so we only get zeros. So this number plus 1 is equal to 0. That's why it is equal to -1. P-adic numbers can express any rational value. When 7 and infinite 6s to the left is multiplied by 3, the result is equal to 1. So this number is equal to 1/3. Now let's go back to normal numbers and look at the problem that most people get wrong. This problem is called the potato paradox and goes like this. There is 100 kilograms of potatoes, which are 99% water by weight. They get dehydrated until they are 98% water. What is the total weight of potatoes after dehydration? Surprisingly, the answer is 50 kilograms. If the potatoes were 99% water, the dry mass was 1%. This means that 100 kilograms of potatoes contains 1 kilogram of dry mass, which does not change, as only the water evaporates. To make the potatoes be 98% water, the dry mass must become 2% of the total weight. So if 1 kilogram of dry mass is 2% of the total weight is 50 kilograms. Now let's look at the probability problem. There are two boxes. In box A, there is one red ball and one green ball. In box B, there are two red balls. Let's say that you take the ball out of the random box. The ball is red. What is the probability that the second ball in this box is also red? If you think that is 50%, you are wrong. To solve this, let's look at all possibilities. If we took the red ball out of box A, there's 100% chance that the second ball is green. If we took the red ball out of box B, we have two possibilities. We either took this ball or we took the other one. In both cases, the other ball is red. In total, we have three possibilities, so the probability that the next ball is red is equal to 2/3, not 50%. Probability can sometimes be counterintuitive, like in a birthday paradox. This problem states that you need only 23 people to have 50% chance that at least 2 of them will have the same birthday. If you have 57 people, the chance that at least 2 of them will share a birthday is already 99%. With 100 people, the chance that at least 2 of them have the same birthday is equal to 99.9999. Matching problem is another problem where probability can be counterintuitive. It goes like this. There are 10 students and a teacher. The teacher has a stack of homework assignments to distribute. The assignments are handed back randomly, which means any student may receive their own assignment or someone else's. What is the probability that no one will get their own assignment? With 10 students, this probability is equal to around 37%. What's interesting is that if we had more students, the probability stays around 37%. Even with 1 million students and 1 million assignments, the probability that no student will get their own assignment is still around 37%. And as we get more and more students, the probability converges to 1/e. The additive persistence of a number is the number of times we have to add its digits to get one digit number. For example, the additive persistence of 167 is 2, because after adding its digits, we get 14, so we have to add the digits once more to get one digit. The smallest number with an additive persistence of 1 is 10. The smallest number with an additive persistence of 2 is 19, and the smallest number with an additive persistence of 3 is 199. But the smallest number with an additive persistence of 4 is 1 followed by 22 nines. And the smallest number with an additive persistence of 5 is 1 followed by that many nines. Sine of pi over 2 is equal to 1. But sine of 1 is an irrational number equal to around 0.841. If we plug integer values to sine function, we get irrational results. Let's add a sine of 2 over 2 to the sine of 1, and add sine of 3 over 3, then sine of 4 over 4, and so on. This infinite sum is equal to exactly pi minus 1 over 2. But even more surprising is that, if we square each term, we still get pi minus 1 over 2. The function we used for this sum is sine of x over x. This function even has its own name, sinc of x. Now let's calculate the alternating sum of sinc for positive integers. This sum is equal to exactly 1/2. If we square each term, we still get 1/2. Surprisingly, even if we cube every term, we still get 1/2. Let's play a game. In this game, we will flip a coin. If it lands on heads, you will receive $1. If it lands on tails, you will receive $5. The question is, how much are you willing to pay to play this game? To answer this question, we can just calculate the expected outcome of one game. We multiply each reward with its corresponding probability of occurring, and then sum them up. Here, we have a 50% chance of getting heads, which results in receiving $1, and a 50% chance of getting tails, which results in receiving $5. So the expected outcome is equal to $3. That means if you pay more than $3 to play this game, you will lose money in the long run. On the other hand, if you pay less than $3, you are expected to win money over time. Now let's modify the rules of the game. Now if the coin lands on heads in the first flip, you win $1. If heads doesn't occur until the second flip, you win $2. If the heads doesn't occur until the third flip, you win $4, and so on. We can calculate the expected outcome of this game. The probability that the first flip will land on heads is 1/2. The probability that the second flip will land on heads is 1/4. The third is 1/8, and so on. When we multiply each outcome by its probability of occurring, we get an infinite sum of 1/2. It means that the expected outcome of this game is infinity. So any price to play this game isn't too high. This is really true. After simulating the game 10 times, the average win is $3.5. After simulating the game 1000 times, the average win is around $5.6. After simulating the game 1,000,000 times, the average win is around $10.4. The more games you play, the higher the chance for big wins. So the real question is, how much are you willing to pay to play this game?